Okay, so I think let us start. This is something new that has happened today. It has been asking me to admit everybody to the class. I don't know. Okay, so in the last class we had started talking about charge particle dynamics, and the last thing that we did was we arrived at an expression for the equation of motion, which we saw was nothing but the Lorentz force. So the equation that we had after extremizing the action in the last class was something like this. Right? And we had seen that E was nothing but grad of phi, and B was curl of A, where phi and A were components of a 4 vector A alpha, right? And we had arrived at, after extremizing the action, this particular equation. And we know that this equation is nothing but the Lorentz force equation. And after that, we discussed that looking at the behavior of E and B, we could categorize E and B as two separate categories and as two separate kind of vectors. We saw that E is going to behave like a polar vector, that's a true vector, and B is going to behave like an axial vector. I don't know what is happening in this. People keep coming in, then I'll have to keep adding people every time. It's going to be a big trouble. Okay, so last time there was a discussion going on where we had to stop, is that why do we have two different categories of vectors? I think, Rajat, what was exactly that we were discussing that you had asked? What was the question?
It was related to the dimension of the two different vectors. So you said that a pseudo vector can be constructed from a tensor of rank 2.
Oh,
But
okay. Yeah, so we were talking about, now I remember. So the discussion was about that why do we have a rank 2 tensor here? Right? That's what I think the question was. That how come we have a rank 2 tensor here? How come one can talk about a higher rank here and not a 4 vector? Okay, so the basic idea remains the same. You have to remember that the whole idea behind putting together, even if you go back, you look at the first 4 vector we introduced to was CT. Okay, so I think the question was more like you have one side you have a polar vector, the other side you have an axial vector, and how can we have two different it was not related to rank, Rajat. It was not related to rank. It was, I think, related to dimensionality that you had asked.
yeah,
The
that
question was
the
related to dimensionality.
rank 2 vector should be of 4 dimension and the other vector of being of 3 dimension.
So the question was that here both quantities are actually three-dimensional, and how come you have a four-dimensional? How come we have something which is now four-dimensional? So if you remember, the way we had put together the idea of four vector exists only when you deal with quantities in four dimension. Now, if you look at this first four vector that we were introduced to, consisted of a scalar and a vector. They are two quantities of very different behavior. You know how do scalars behave under linear transformations. We know how do vectors behave under linear transformation. We know scalar is a quantity. By definition, we define something as a scalar which remains invariant. On the other hand, we know how a vector, but when we put them together is when we form a four vector. Right? This is separately three-dimensional. This is CT. How come they why are they put together? They're put together because we saw that the quantity that is invariant under what you define as Lorentz transformation is a quantity which is a combination of this scalar and this vector. In the same way, we will realize that when you have something like a polar vector here and an axial vector here, right? Last time, you remember, I showed you that if you have a tensor of rank 2 and an antisymmetric tensor of rank 2, particularly, we discussed this in the last class, that if you have an antisymmetric tensor of rank 2, then that antisymmetric tensor of rank 2 can be written down. Its components can be written down as a combination of and here I had axial vectors, components of an axial vector, right? So if you have in four dimension, if you construct a quantity like this, whose components, these time components are basically polar vectors and its spatial components are basically your components of a axial vector, then a quantity is formed which is an antisymmetric tensor of rank 2 in four dimension. And you will realize that out of this quantity is that I can construct something which remains invariant under Lorentz transformation. So whenever we are dealing with Lorentz transformation, you will realize that E itself is not invariant under Lorentz transformation, or some combination of E only is not invariant under Lorentz transformation, or B alone is not invariant under Lorentz transformation, or some combination of B itself is not invariant under Lorentz transformation. First thing. Second thing, that how E and B will transform under Lorentz transformation. You will realize that E and B will not transform as a vector or a scalar or something else under Lorentz transformation, but they will together have a certain kind of behavior under Lorentz transformation. So if you put all these things together, you realize that you can, in four dimension, you can define a tensor of rank 2, whose we will see time components will actually be this polar vector, just like A alpha beta, and its spatial components will be components of this axial vector, is going to be a quantity which is going to transform like what the way something transforms under Lorentz transformation, right? It is this quantity together is what is going to follow your Lorentz transformation, first thing. And second thing, it is out of this quantity, F alpha beta, is that you will be able to construct something which will be invariant under Lorentz transformation. So that is why when you look at something under Lorentz transformation, keeping in mind the idea of Lorentz transformation, you see that E separately or B separately have no existence under Lorentz transformation. It is only that they exist as components of a second rank antisymmetric tensor in four dimension is the way they actually transform under Lorentz transformation, right? So we're going to arrive at that expression a little later. So definitely it is dimensionality. It's dimensionality. The way, I mean, if you want to put them together, the dimensionality is actually four dimensional in Minkowski spacetime, and they are going to be components of a second rank tensor in four dimension. Right? Okay, so let's leave this here. We'll come back to talking about this later because we were discussing this in the last class. I thought that we should not leave it hanging. Okay, so I go back to what we were discussing in the last class, is that we had this expression for Lorentz force. one can actually calculate the amount of work done or talk about the energy contained in the energy that a particle will have, or what would be the kinetic energy of the particle moving in an electric field just from this equation. Right? So if I do, now you remember expression for kinetic energy of the charged particle. We obtain this is actually this. If I do d by dt, right? You do d by dt of this, do it very carefully. Mc square is pulled out. You do a derivative of this with respect to time. And you can actually show, we've worked this out when we were doing for the force, is that d by dt of kinetic energy, that is rate of change of kinetic energy, is equal to v dot dp by dt. If I substitute for dp by dt from here, this is nothing but dp by dt, then in fact this expression was not mdv by dt, sorry, it was actually dp by dt. It was only for Newtonian physics that left hand side reduces to mdp by dt. Otherwise, Lorentz force was actually dp by dt. So I have E plus E by C V cross V. And naturally, this gives me that dE kinetic by dt is E V dot V, or I can actually calculate the amount of work done in time dt. From here, what will that be? V dt is nothing but E dr dot E. So you see that if you have a charged particle moving in an electromagnetic field, there are two things that you can analyze from this result. First thing is that the work is done only by an electric field. We know that. This is true because if you look at the force exerted by the magnetic field, it's always going to be perpendicular to the velocity. Hence, V dot V cross V term is 0. So magnetic field does no work. And the amount of work done in time dt is this expression. You have seen this expression in your electricity magnetism class also. Right? So I can calculate the amount of work done in an electromagnetic field on a charged particle. We'll need this expression little later. Is there anything anybody wants to ask at this point? Anything that is not clear at this point? Okay, fine. If this is okay, then I want to discuss few more things before we actually start looking at motion of or trajectories of charged particles in electromagnetic fields. What I want to first discuss are two very important things that we started with when we were discussing classical dynamics. First thing was time reversal. If you remember, I told you when we started, and this was a big discussion that we had in the first two classes when we started this course on classical dynamics, that we saw that if you look at Newton's equations, or if you look at classical law, or you look at any physical law for that matter, in that we've been dealing with, you change t to minus t, that is you do time reversal, your equations or your laws or your Newton's equations, they remain invariant. This was something very important that we saw in the beginning of classical dynamics. Right? You see, even here, if I look at my equations of motion, you remember V is dr by dt, and dp is actually something of the kind right? So when I change t to minus t, for this equation to remain invariant, if I impose time reversal on these equations, you see that in addition that these equations will remain invariant under time or under time reversal if and only if, along with t going to minus t, I also change b to minus b. This is a very important property because b is not a pure vector. B is actually an axial vector, right? It's not a true vector. It's an axial vector, right? It's very important to see that if you look at this is d square r by dt square, you change t to minus t, left hand side remains invariant. There is no time dependence here. If you look at this quantity, then you look at the fact that when you change t to minus t, you also, for this term, to change to remain invariant, you need to do b to minus b. So what does really time reversal mean? I'll just remind you. Time reversal meant that if the motion proceeded in one direction, I reverse the time and I look at the motion going in reverse direction, it is possible to do such a thing in classical physics, right? So, or reversibility was a very important aspect from classical dynamics, right? So for these equations to remain time, to obey time reversal, it is very important that in addition to doing t to minus t, you should do b to minus b, or phi will remain phi, but a should be changed to minus. You can see that here also, if you add that term in E, and you see E as combination of del A by del T grad phi, you see that as you do the time reversal, you need to keep phi to phi, but you need to change. So if you change t to minus t, E remains E, but B has to change its sign. Or if you look at it in terms of potentials, phi remains minus phi, but phi remains phi, but A has to reverse to minus A. Then these equations will obey time reversal. So it is very important to see what happens to these equations under time reversal. First thing. Second important thing is what we've already discussed. I just want to discuss it here once more from viewpoint of four vectors is gauge invariance. The other kind of invariance that we impose. We've not talked about why really one requires gauge invariance. The idea of gauge invariance actually arises in quantum field theory, and gauge invariance is a very important concept. It is actually what is responsible for conservation of charge in quantum field theory. That if you look at yes,
Ma'am,
yes, Sanchi.
could you please add Claire, because she's been trying for like 10 minutes now.
I can't see Claire's name here.
She's not okay. Cool.
I can't see her.
Okay. Maybe it's the internet problem. Okay.
I don't know what happened to my.
You can just go to your manage participants option and then disable the waiting room option.
But I can see manage participants. Claire is not there.
Okay.
I can't
No,
see.
I'm saying for like, yeah, you don't have to add then if you disable the waiting room
No,
option.
because the name flashes that I have
Okay.
to admit somebody. But you know, when I'm teaching, I don't realize that somebody is waiting to be added.
Okay. Okay.
Because I always minimize everything else. I just keep my screen visible. That's it. Okay, so the after time reversal invariance, there is one more thing that we have talked about is gauge invariance. Right? I want to revisit gauge invariance. We had talked about gauge invariance when we did charge particle dynamics in classical dynamics for a classical particle, but I'm going to now do it one for a relativistic particle, first thing. Second thing, I want to do it from viewpoint of four vectors, right? So what was really gauge invariance? So let's say if I have a function f, which is a function of time and position coordinates. So it's a function of four vector, let's say x alpha. Then gauge invariance means that this four vector A, let's write it as covariant, is ambiguous. In other words, that if I make a change in this four vector, A alpha, that is my original A alpha, I change it to A alpha minus covariant derivative of this function f, my equations of motions do not change or my physics doesn't change. Right? How can I show you this? Is that, let us see how does this transformation of changing A alpha to A alpha minus del alpha f changes my equations of motion. Now changing my equation of motion would mean is to see how does this change my action, right? Because action is the starting point for arriving at my equations of motion. Now this change, if you go back and you look at your action, is just going to add a term my action is going to change by this term, but then this term, if you look at what is this is del alpha f dx alpha, is nothing but differential of d alpha. And then when I look at this in with respect to the integral, we've already seen that if I add a total differential, we've talked about this, to our action. If I add a total differential to my action does not change. So this kind of quantity is not going to change my action, and hence any transformation of this kind, any transformation of this kind will have no effect on my equations of motion. Now, my equation of motion does not depend on A and phi, but my equation of motion depends only on E and B. So that means that if I make a change like this, if I make a change like this, which amounts to changing, let's say, A vector to grad of this f and phi to phi prime, which is phi original minus 1 by c del by del t f. My E and my B will remain invariant. Will remain invariant. This is known as a gauge transformation. And this whole idea, the fact that E and B, and hence my equation of motion, do not change or are invariant, is what is known as gauge invariance. Is what is known as gauge invariance, right? So that means that if I change my first thing is that means my A and phi are not uniquely determined. I can always, it is always possible to redefine my A as some A plus gradient of some arbitrary function f. There is no set form of f that I started with. It is some arbitrary function of x alphas. If I can change my A to A prime, which is A plus grad f, and my phi to phi prime, which is phi minus 1 by c del f by del t, then my E and B will remain invariant, right? So these two invariances, when you look at classical electrodynamics, relativistic electrodynamics, are very important. First is time reversal. For your equations to hold true under time reversal, that is t going to minus t, your E will remain E, but your B has to go to minus B. Then your equations remain invariant, first thing. Second thing, that any gauge transformation will leave my equations of motion invariant. So A prime, A and phi are undetermined or cannot be uniquely determined up to this arbitrary function f. You have to keep these two things in mind always. Why? Because we will very often exploit, in fact, you very often do it without realizing, your choice of gauge to simplify your problem in classical electrodynamics. You very often do that, right? Now, one simple problem that we are going to pick today, you will see that in that very simple problem also, you utilize this idea of gauge invariance, right? Now, since this class, this session is going to end, I'm going to restart, and I'm going to restart at this point. So you take 4 or 5 minutes till the time I restart to go through what we've done. If you want to ask anything, we can have a discussion. I don't know now if I restart whether you will have to again put the password or not, or whether I'll have to readmit people again or not. But let me just do that anyways, right? So you can just go through what we've done, and I'll just restart the class.